What do we actually understand about the human brain, and what can nobody explain? In this video, we'll explore the top of both lists. But first, we have to start with how much of the brain we've mapped. This is the most detailed picture of a human brain that anyone has ever made. It took 1.4 petabytes of data to store. That's about 1.5 million gigabytes for one picture. And this is all the brain it covers. A grain of sand. 1 cubic millimeter out of a brain that holds about 1 million of them. That's where we really are with the human brain. And in that one grain, we found two things nobody can explain. In a piece of tissue we can't even be sure is normal. Start with the connections. Most of the neurons in that sample did what the textbook says they should, reaching out and touching another cell once, maybe twice. Thousands of weak little handshakes. But scattered through the tissue were pairs of cells joined by up to 50 synapses, 50 separate connections between the same two neurons. In a network built out of weak, spread out contacts, that is a very loud, very private line between two cells. Nobody predicted them. Nobody can tell you what they're for. Here's where the sample came from. It matters later. A woman was having surgery for epilepsy, and a small piece of her temporal cortex was removed, the region running along the side of your head just above your ear. Instead of being discarded, it went to Jeff Lichtman's lab at Harvard, working with Google. They shaved it into about 5,000 slices, each a fraction of the thickness of a hair, and photographed every one under an electron microscope. It came out in Science in 2024. Inside that grain of sand, about 57,000 cells, 150 million synapses, and 9 inches of blood vessels, coiled up in a speck you could lose on your fingertip. Then there was the second thing nobody expected. In a small number of places, axons, the long cables that carry a neuron's signal away, were wound into tight coils, whorls, wrapped around themselves, going nowhere obvious. If those are normal, then there's a piece of standard human brain architecture that we have never once seen and have no account of. Except we can't say whether they're normal. Remember where the tissue came from. That brain belonged to someone with epilepsy. So when the team saw those coils, they couldn't tell whether they were looking at a rare feature of healthy brains or at something the disease had done. They say so in the paper. The most detailed image of human brain tissue ever produced, and we can't be certain it's a picture of a normal brain. Not through carelessness. Because you cannot simply obtain a cubic millimeter of healthy human cortex. It has to come out of somebody, which means it comes from surgery, which means it comes from illness. So let's do the arithmetic everybody does next. 1 cubic millimeter took 1.4 petabytes. A human brain is about 1.2 million cubic millimeters. Multiply it out, and that sum is ours, not the paper's. And a whole brain at that resolution lands near 1.4 zettabytes, roughly the size of all the data on the internet. Which points at an obvious answer. We just need more. Bigger microscopes, cheaper storage, time. And the trend is on that side. In 20 years, the volume we can map at this resolution has grown by a factor of 1,000. But there's a harder question underneath it. Suppose we had it, all of it. Every cell, every synapse, every coil. All 86 billion neurons and their 100 trillion connections sitting on a drive. Would we understand anything? You can't judge what's missing until you've seen what a real explanation of a brain actually looks like. So start with the ones we've got. There are 5 of them. What we know. Number 1, the nerve impulse. There is a set of equations that will tell you, correctly, what a nerve cell is about to do next. Alan Hodgkin and Andrew Huxley worked them out in the early 1950s on a squid whose nerve fibers are big enough to push a wire down the middle of. Sodium rushes in, potassium flows out, a pulse of voltage runs down the cable. 70 years on, those equations still hold. That is as complete as biology gets. And it came out of a single nerve fiber. What we know. Number 2, how you see. A glass slide slipped through a projector by accident, and a cell fired like a machine gun. David Hubel and Torsten Wiesel had been recording from cells in the visual cortex for months, getting almost nothing. That cell didn't care about the picture. It cared about the edge of the slide, a line tilted at one particular angle. Your visual cortex doesn't receive an image the way a camera does. It builds one, out of cells watching for lines and movement, stacked into shapes, objects, faces. Nobel Prize, 1981, from one cell. What we know. Number 3, movement. In 2025, a man who had lost the ability to speak sat in a lab and thought of a sentence, and the sentence appeared on a screen. The electrodes were in his motor cortex, the strip running ear to ear over the top of your head, the part that turns "I want to" into "I did." A team at Stanford did this with 4 volunteers, pulling sentences from a vocabulary of 125,000 words, about 74% right, when the person only imagined saying them. It works because that strip of cortex is genuinely understood. What we know. Number 4, place cells. There are cells in your head firing right now, purely because of where you're sitting. Move to the next room and a different set takes over. John O'Keefe found them in 1971 and called them place cells. Then May Britt and Edvard Moser found cells one step upstream, firing in a repeating hexagonal grid, like graph paper laid over the floor. A literal map made of cells. Nobel Prize in 2014. And both have since been recorded in people during surgery. What we know. Number 5, making memories. A man sat down every day to trace a shape in a mirror, and every day he got better at it, while insisting every time that he had never done it before. His name was Henry Molaison. In 1953, most of his hippocampus was removed to stop severe seizures. It worked, and it cost him the ability to form new, lasting memories. You'll still remember this sentence tomorrow. He couldn't, and some part of him was learning anyway. Brenda Milner spent decades with him, and that one patient taught us memory isn't one thing. Now look at what those 5 have in common. 1 squid fiber, 1 cell, 1 patient. Every real explanation on that list came out of something far smaller than a whole brain, which is the first hint that the problem was never only size. Now the other list. What we don't know. Number 1, what a memory is. Right now, you could bring back a room you haven't stood in for 20 years. That memory is made of matter sitting in your head. In mice, researchers can tag the exact cells active during learning, the engram, the physical trace, then switch them on later and watch the animal behave as though it's remembering. And still, ask which property of that tissue holds the content, and there's no agreed answer. Someone put the question to a few hundred neuroscientists. About 70% agreed memories live in the pattern and strength of the connections. On which feature does the storing? There was no consensus at all. What we don't know. Number 2, why we sleep. We know where the room is filed. We don't know what the room is made of. You'll spend around 1/3 of your life doing it, and going without it will kill you faster than going without food. We know a great deal about what happens during sleep. What it's for is still argued over. Is it for repairing cells? For filing what you learned that day? Or for rinsing waste out of the brain? The idea that got the most attention this past decade, until a later study went looking for the same effect and couldn't find it. Each has evidence. None has won. What we don't know. Number 3, why we dream. Stay inside the same night for a moment. 6 years. That's roughly how long you'll spend, across a life, watching films your brain made without asking you. Freud said they were disguised wishes written in code. That hasn't held up, and what replaced it doesn't agree with itself. One account says a dream is the day being replayed and filed. memory, caught in the act. Another says the brainstem fires more or less at random during REM sleep, and the cortex, which can't help itself, builds a story around the noise. So the dream isn't the point, it's the wallpaper. Either your dreams are your memory doing its job, or they're your brain talking in its sleep. Nobody can tell you which. 3 items in, and we've already hit sleep and dreaming. 2 things you'll do tonight that nobody can fully explain. If that's the kind of gap you enjoy sitting with, subscribing is how the next one finds you. What we don't know. Number 4, anesthesia. In 1846, in an operating theater in Boston, a surgeon removed a tumor from a man's neck while the man felt nothing. A dentist had put him under with ether. It's been routine ever since. Hundreds of millions of times a year, we take a person's consciousness away and hand it back, reliably enough that you'd let someone do it to your child. We still can't say how. One account says anesthetics dissolve into the fatty membranes around cells and disturb them. The newer one, now ahead on points, says they bind directly to proteins on the neuron's surface. 180 years in, Science magazine still lists the mechanism among its major open questions. What we don't know. Number 5. What glia do. About half the cells in your head aren't neurons at all. They're glia. And for a century, the job description was maintenance. Wrap the wiring in insulation, feed the neurons, mop up chemicals, hold the blood-brain barrier together. Real work, but support work. The open question is whether that's all they do. There's growing evidence that astrocytes, the commonest kind, take an active part in how signals get passed around. If that turns out to be right, then half the brain has been filed under maintenance while it was sitting on the committee. And the map we're so carefully building would have been drawing the wiring while skipping the wiring's neighbors. Put those 2 lists side by side and something shows up. Everything on the first list is a mechanism. How a signal moves, how an edge becomes an object, how a cell marks a place. Everything on the second is a question about what something is or what it's for. And notice we can do nearly everything on that second list. We put people under and bring them back. We sleep, we dream, we remember. We just can't explain any of it, which is a peculiar sort of knowledge, being able to work something you don't understand. Neither list is anywhere near complete, by the way. You could fill an afternoon arguing about what belongs on them, and neuroscientists do. But swap the items in and out and the same split survives. We have been extremely good at the machinery, and we have barely started on the meaning. So, back to that grain of sand, and to the woman it came out of, who we know nothing about except that she was ill enough to need surgery. We looked at a piece of her brain more closely than anyone ever has, and what we got was 2 things we couldn't explain, in a sample we can't be sure is typical. That's not a failure. That's what looking closely at something new does to you. But it should change what we expect from the finished map. Because a map is a description. It tells you what is there. It doesn't tell you what any of it is for. We will almost certainly get the whole picture eventually. Every cell, every connection, the lot. Whether that will feel like an answer or like a very detailed photograph of a question is the part nobody can tell you yet. There's a new question like this one here every week. The last one didn't stop at the brain. 9 things science still can't explain, and not one of them settled either. I'm Ponder. I'll see you at the next question.